Hey guys, welcome back. So showing you some really cool stuff here. This is the a squared plus the b squared and how those two areas will fill up the exact same volume as the c squared there, which is absolutely fascinating. So this is a demonstration of the Pythagorean theorem. So we're going to be doing a review for the Pythagorean theorem and special right triangles. So it's quite a lot of material, but hopefully at least the Pythagorean theorem, you've definitely seen that before. If you haven't seen special right triangles before, if you missed those videos, it's not the end of the world. You can actually do trig instead of the special right triangles, but the special right triangles will kind of help. So not a complete deal breaker. Just focus on making sure you understand how to do the Pythagorean theorem part, and it would be good for you to know the special right triangles. But as long as you got the trig part down, which we did in class, you should be okay for the test. You can actually go ahead and take the practice test as well to make sure you know how to do all those problems. And you'll be good. So just a quick thing real quick, we'll see that if the side lengths of A plus the side length of B, if they are less than or equal to the C, then they're too short and they don't actually meet and they won't actually form a triangle. So that's one of the things we showed with we showed earlier. Anyway, so if the a squared plus the b squared is equal to the c squared, when we make a square out of the a length and the b length, we add them together, those will fill up the exact same as the c squared. That's when it's a right triangle, which is actually kind of cool. That's a Pythagorean theorem, or the converse of the Pythagorean theorem, because it's backwards. All right, then if the a squared plus the b squared is greater than the c squared, that's an acute triangle, meaning this angle here is not a right angle. The largest angle is acute. Then if the a squared plus the b squared is less than the c squared, meaning the c is so long that when we square it's bigger than the a squared and the c squared, the a squared and the b squared, that's an obtuse triangle. So we'll get into that in a little bit more detail in just a second. So here we go. All right, so the Pythagorean theorem says that if it's a right triangle, meaning if we have a right angle between the two legs, then it is then we know the a squared plus the b squared is equal to c squared, just like we saw in the last one, which is kind of cool. The converse, like shoes on the wrong feet, is when we switch the order. So if a squared plus b squared is equal to c squared, then that means it must be a right triangle, and that's the converse of the Pythagorean theorem, which allows us to prove whether or not something is a right triangle if a squared plus b squared, sure enough, is equal to the length of the c squared, the length of c squared. Okay. So we can classify triangles by their angles. If it's an acute triangle, obtuse triangle, right triangle, equiangular, when all the angles are the same. So we classify the triangles by their angles by their largest angle. So again, the small side is opposite the smallest angle, the medium side is opposite the medium angle, and the longest side will always be opposite of the longest angle. So look at the longest angle, or the longest side. Opposite of that is your largest angle, and if that is acute, then it's acute triangle. If your largest angle is obtuse, then it's obtuse triangle. If the largest angle is a right, it's a right triangle, and if they're all the same, then it's equiangular. So looking at the converse of the Pythagorean theorem, is this a right triangle? Well, if the a squared plus the b squared is equal to the c squared, then that means this has to be a right triangle. So let's look at our two small sides, 6 squared plus 6 squared. That's going to be 36, 36, 72, and then 9 squared is 81, right? Okay, so this is not equal to the c squared, so that means that this cannot be a right triangle. But then what kind of a triangle is it? Well, it's actually an acute triangle, but we'll figure that out in just a second. So what if it's a not triangle? Like what if it's an equilateral triangle where all the sides are exactly the same? They're all a. Well, then whenever we plug in the a squared plus b squared is c squared, they're all the same thing, right? So it's a squared, the smallest one, the medium one of a squared, and the longest side of a squared. Okay, well, a squared plus a squared is 2 a squareds, and that's going to be twice as big as only 1 a squared. So whenever the a squared plus b squared is greater than the c squared, like we have here, then it has to be an acute triangle. And the best way to remember that is just remember the equilateral example, because 2a squared is twice as big as 1a squared, which is an acute triangle. All right, so what kind of a triangle is this one? We got 5, 6, and 7. Well, 5 plus 6 is 11. That's longer than 7, so they do actually meet to make a triangle. That's good. But then what kind of a triangle is it? Well, opposite the longest side of 7 is the largest angle, which is the angle in question, right? So let's fill it in. We got 5 squared plus 6 squared is some relationship to 7 squared. Well, that's 25 plus 36, which is 61, and 61 is larger than 49. So this is not a right triangle, and remember, if it's larger than that, it has to be an acute triangle, just like what we saw on the last part. All right, so if the a squared plus b squared is equal to the c squared, then it's a right triangle. It's the converse of the Pythagorean theorem. If they're greater than the c squared, then it's an acute triangle, just like we saw in the equilateral example. Just like right here. So a, and a, 2a squared is twice as big as 1a squared, which means these two added up to be more than that one. Okay, then what's left? Well, if the a squared plus b squared is less than the c squared, the only other thing it can be is an obtuse triangle. And that's because the c is so long that when we square it, it's larger than the a squared and the b squared combined. It means it has a really, really long side, which would make it obtuse. So what kind of triangle has these side lengths? Alrighty, well, the square root of 51 is close to 7, so 7 plus 3 is 10, and that's bigger than 8, so we're good to go. It is actually a triangle. The next part we want to do the 3 squared plus rad 51 squared is some relationship to 8 squared. 8 squared 64. Whenever we square a square root, they undo each other, right? So rad 51 times rad 51 is just regular 51. So 51 plus 9, which would be 60. So 60 is less than the 64. So if the C is so big, it's bigger than these two, this is an obtuse triangle. All right, so now we're going to look at our special right triangles. So if it's a right triangle, in this case it is, this is when it's an isosceles right, where these are both 45 degrees, right? The base angles are congruent, and let's let both of these sides be 1, because that's the most simple one that we can make, right? So then we have 1 squared plus 1 squared is equal to x squared. So what's the length of that hypotenuse? You probably already know, 1 radical 2, right? But this is how we did it. So 1 squared plus 1 squared is 2, and that 2 is equal to x squared. So we undo a square with the square root, and so if I take the 1/2 power one side, I have to take the square root of the other side, so x is equal to the square root of 2. So our special right triangle, 45, 49, and 5, 90 triangle is 1, 1, and radical 2. All right, so the 1, 1 radical 2, that's going to be the same regardless of how we scale up or scale down this this triangle. They're always going to have the same extended ratio of 1, 1 radical 2. So if we multiply it by 3, it's now 3, 3, 3 rad 2. If we multiply it by 4, 4, 4, 4 rad 2, multiply by 5, 5, 5, 5 rad 2. And even if we multiply it by some reduction, a scale factor less than 1, like cutting them all in half, it's 1/2, 1/2 radical 2 divided by 2. And there's infinitely many reductions and infinitely many enlargements that we could do. Any k larger than 1 or less than 1, any real number, rational numbers, irrational numbers, it doesn't matter. We can multiply it by anything. It's kind of cool. All right, so the other special right triangle we have is half of an equilateral triangle. So if we have an equilateral triangle where each side we let it be equal to 2, then half of that would be 1 down here. So we have 1 and 2. The only other thing we have to do is solve for the height of the equilateral triangle when one of the side lengths is 2. So it is a right triangle, so we can solve for that using the Pythagorean theorem. Our hypotenuse is 2, so it would be 2 squared. We're going to call this length here that we're solving for, we're going to call it x. So we're going to say that we have x squared plus 1 squared. So, or 1 squared plus x squared is equal to 2 squared. So we subtract the 1 squared from both sides, leaving us with x squared is equal to, that's 4 minus 1, which is 3. All right, then the other thing we have to do after that is we take the square root of that, square root of both sides, which will leave us with x is equal to the square root of 3. So this is equal to rad 3. So you probably remember that. It's 1, 2, radical 3. But remember, radical 3 is approximately 1.71. So it's actually less than 2. And if you think about 2 is really the same thing as square root of 4. And obviously the square root of 4 is going to be bigger than the square root of 3. So don't get that messed up. Our longest side is 2, shortest side is 1, radical 3 is the intermediate or the middle side. So this is going to have an extended ratio of 1, radical 3, 2 if we do it in order from least to greatest. All right, that same thing, the 1, 2, radical 3 is going to be exactly the same no matter how large we scale it up, even times 3, and no matter how small, even going down to scale factor of 0, going all the way to infinitesimally small, or like infinitely small. Whatever, you get the idea. All right, so let's go ahead and get started on the assignment. So as a review in about 10 minutes, it wasn't too bad, but it is a lot of material. Obviously, it's better if you go back and actually do those assignments and watch those videos and get all that practice with the homework. But if not, then this will at least help get you ready for the test that we're going to take in person next week. All right, on number 1, we have lengths of x and 8, and then the hypotenuse is the square root of 104. So since this is a right triangle, we can use the Pythagorean theorem to solve for the missing side length. So our two legs are going to be x and 8 squared, and then our hypotenuse is radical 104 squared in this case, so for the Pythagorean theorem. The next thing that we're going to want to do is subtract the 8 squared from both sides. So that's going to leave us with x squared is equal to, now if we square the square root of 104, they undo each other, leaving us with just 104. So that's going to be 104 minus 8 squared. Now 8 squared is 64, so 104 minus 64 is just going to be 40. So we're left with x squared is equal to 40. Now we don't want x squared, we want just x, so we end up taking the square root of both sides. So the square root of 40, if we put it in a calculator, is approximately equal to 6.32, and that'll be your answer for x in this case. Looking at number 5, don't be tricked on this one. The hypotenuse is the longest side that's on the bottom because it's opposite of our right angle. So when we plug this in, we're going to have 2 rad 10 squared plus a radical 60 squared is equal to x squared. So we're solving for the hypotenuse. Now when we square a radical, this is just going to be 60, right? But on the other side here, it's like we're multiplying it by itself. So that's 2 rad 10 times 2 rad 10. Now, when we multiply radicals with coefficients, if you remember, we multiply the parts on the outside of the coefficients, then we multiply the parts on the inside of the coefficients. Same way we reduce radicals with division as well. So 2 times 2 is going to give us 4, and then rad 10 times rad 10 is just a regular 10. So we have 4 times 10, which is 40. So this part here, this component is going to be 40 plus 60, which is 100, right? So x squared is 100. Take the square root of both sides. So the square root of 100 is going to be is equal to 10. All right, number 7, this, now we wanted to decide what kind of a triangle is it, right? So just in a quick review, if the A plus the B is less than the C, then it is not a triangle. That's because they're too short. So if we add these together, two shorter sides is 20, that's bigger than 16, so it's going to make a triangle. That's not a problem. Then we can check what kind of a problem it is by looking at the converse of the Pythagorean theorem. So if the a squared plus b squared is equal to the c squared, it's a right triangle. If they're greater than that, remember like an equilateral example, 2a squared is twice as big as a squared, then that's going to be an acute triangle. And if the c is so big that's bigger than the a squared plus b squared, it's an obtuse triangle. So on this case, we can just plug that right in the calculator. 9 squared plus 11 squared is going to be 202, and 16 squared is 256. Now this is less than that, which means the c is so big it's larger than the a squared and the b squared, which makes this an obtuse triangle. Number 9, if we check this, 6 plus 6 is 12. That's going to be equal to it, which is less than or equal to 12. So they're not going to be long enough sides to actually make a triangle. If you think about it, the 6 and 6, they're going to meet, but they meet on the 12, the midpoint of the 12, right? Which isn't going to be a three-dimensional triangle. Now, if this was a little bit longer, like say this was 6.5 or something, then it would actually meet and it would make a triangle, which is pretty cool. So this is not a triangle. Number 16, now we're doing some special right triangles. This is isosceles because these two sides are the same, so it's 45, 45, 90, meaning it's similar to 1, 1, radical 2. We just have to figure out how much bigger or what our scale factor is. So look at the corresponding leg of 1 turns into a leg of 6, so it's being multiplied by a scale factor of 6. So for SF scale factor, you can put 6 on that one. All right, so then what's x going to turn into? Well, radical 2 times 6 is 6 radical 2. All right, number 24, this is a 45, 45, 90 right triangle. So it is similar to 1, 1, radical 2. We have a leg length of 1, which turns into a leg of 24. So our scale factor is equal to 24. Then the next part we want to know is what is this length here going to be? Well, that's another leg, and it's got to be the same thing. So that's got to be 24. But that's not our answer because the length of x includes the height above their eyes, which is 5 feet. So we add 5 feet to that, which will give us 29 feet altogether for the length of the flagpole x. Number 22. So on this one, this is a 30, 60, 90. So it's similar to 1, 2, radical 3. The smallest angle is opposite the smallest side of 1. The hypotenuse is 2, and then the intermediate one would be the radical 3. So on this one, we're going from rad 3 to a 21. So this is going to be a little bit challenging to find the scale factor. So how do we go from a radical 3 to a regular 3? Well, we have to multiply it by a scale factor of radical 3. Now we have regular 3. How do we go from regular 3 to 21? Now we multiply it by 7 more, right? So altogether, our scale factor is 7 radical 3. So what's going to happen to the hypotenuse length of 2? Well, 2 times 7 radical 3 is now going to be 14 radical 3. So our scale factor is 7 rad 3, and x is going to be a length of 14 radical 3. Last one I want to do with you is number 30. Still doing really well on time. We've got two special right triangles, 45, 45, 90, and 30, 60, 90 over here. So go ahead and fill those in. I want you to write 1, 1, radical 2 on this one, and then 1, 2, radical 3 on this one. Now look at the corresponding sides. They tell us this is 4, this length is 7, so that means this is 3 more than the other one if we subtract the 2, right? So if I'm going from 1 to 3, my scale factor is 3. So 2 is going to turn into 2 times 3 is 6. Radical 3 is going to turn into 3 times rad 3, which is 3 rad 3. Now notice this 3 rad 3 is the exact same as this 3 rad 3, right? That was kind of smooth. So how do we go from a leg length of 1 to a leg length of 3 rad 3? Well, we multiply it by 3 rad 3. So the other one is times 3 rad 3 is going to be 3 rad 3. And then the hypotenuse of radical 2 times 3 rad 3. Well, if you remember on that, we multiply the parts in the inside of the radical and the parts on the outside separate. So 3 times 1 is 3. Rad 3 times rad 2 is now going to be radical 6. And we can't reduce that because those are not the same. So we're left with 3 radical 6. Now the question asks for what's the perimeter of this shape, and you're going to have a question very similar to this on the test, so we need to make sure we know how to do this. The perimeter, we just add links all the way around the side, so we don't actually need the sides in the middle, we just need the ones on the outside. So we got 7 here, 6 here, and 4 here. So if I add all the constants together, that's going to be 17, and then if I add the radicals, that's 3 rad 3 plus 3 rad 6. Those are not the same radicals, so we can't combine them together. So our final answer is 17 plus 3 rad 3 plus 3 rad 6. 17 plus 3 rad 3 plus 3 rad 6. And again, those are not like terms, they're not the same radical, so we can't add them together. All right, so that's it. If you have any questions, please let me know. Make sure you do the practice test. If you're an A-track student, make sure you do it on Friday, please. And if you're a B-track student, make sure you do it at least Tuesday or Wednesday before we take our test on Thursday or on Monday, the first day back that I see you guys next week. Then the second day back, we'll play a game, the second part of our golf game, which I think you guys will really enjoy. It's going to be a lot of fun. And then we have spring break. So if you are all caught up on your homework, you're going to really enjoy your spring break. It's going to be awesome. If you're not caught up on your homework, then you got some splaining to do, and I'm going to have to make some unfortunate phone calls home, and you might not enjoy your spring break as much as you wanted to. So